This is notes for the ICP unit on waves. This will be the first day of notes for this unit. In this unit we'll talk all about different kinds of waves, all the way from water waves to sound waves to light waves and everything on any side of that. So you can see in this picture right here you've got water waves up in the corner, and you've got everything from sound waves to light waves to X-rays and even gamma radiation like you can get from nuclear fallout. All of those count as waves. So we're going to talk all about those. So we'll start with a little bit of vocabulary so we have what we're talking about. First of all, a mechanical wave. There are really a couple kinds of waves. A mechanical wave is the kind that moves matter. So a water wave would be a mechanical wave. Waves, again, just like everything we've been talking about recently, are a source of energy. A wave is moving energy through whatever it's running through, and that what it's going through is called a medium. So the medium, that's the material through which the wave is moving. That would be water, or it could be air, it could be your eardrum. That's where the waves are happening. Every wave has a peak and a valley, the highest point and the lowest point. The highest point is called a crest, the lowest point is called a trough. So a crest and a trough, high and low. And the length of time that it takes for a wave to happen is called a period. So if you're standing there and it takes 1 second for every wave to pass you, the period for that wave is 1 second. Just like the period for this class is 52 minutes. Okay, now we're going to look at an individual wave and what happens with an individual wave. So frequency is how often you do something. So for a wave, that's how often waves pass. So if you're standing in the water somewhere and you're having waves pass you every second, that's the frequency of waves. That's 1 per second. Hertz is the units we use for waves. So if it passes at 1 time per second, that's 1 hertz. You might have heard of 60 hertz noise or 60 hertz electricity. That means there are 60 waves per second. The wavelength is just what it says. It's the length of the wave. So if you've got a crest on one wave and a crest on the next wave, from the top of the crest to the top of the next crest is 1 wavelength. And how tall the wave is the amplitude. So a tsunami has a very large amplitude. It's a very tall wave. A wave in a pond is never going to get very tall. The height of the wave is its amplitude. Now if you know the wavelength and you know the frequency, you can measure the speed of the wave. Wavelength times frequency is speed or velocity, and that equation looks like velocity equals wavelength times frequency. So notice that frequency is f, wavelength is this funny looking character called lambda. It's a Greek symbol, kind of looks like an upside down backwards y. Alright, so here's a wave and all the definitions on it. So there's a wave going up and down here, and from here, from the peak, the crest, to the peak of the next wave, the crest, is 1 wavelength, and the time for that to go past is the period of that wave. You see that the amplitude is how tall the wave is, so from the middle of the wave to the top of the wave is the amplitude. There's the crest, there's the trough, In this case, the wave, all of this is happening in 1 second. So if all of this happens in 1 second, and you have 1, 2 waves, that's 2 waves per second, that's 2 hertz. So here's an example problem. If you go to a wave pool and you've got a wavelength that's 3.2 meters, which is a little over 10 feet, and its frequency is 0.6 hertz, that's 0.6 per second, so about every 2 seconds it goes by. Velocity is wavelength times frequency. The wavelength is 3.2 meters. The frequency is 0.6 hertz. So if you multiply those two together, you get a velocity of 1.92 meters per second. All right, 2 kinds of waves: longitudinal waves and transverse waves. The easiest way to look at this is probably with a slinky, and we'll get a giant slinky out next week and we'll see these things in action. A transverse wave is one that makes the medium, the stuff that it's going through, vibrate at right angles to the wave. So if you take a piece of rope and you tie it to a doorknob and you yank the end of the rope once, you'll see a wave move through the rope. That wave moving through the rope is perpendicular to the direction of the wave in which direction it's going. So that's a transverse wave. A longitudinal wave is a wave where the vibration goes the same direction as the wave. So if you look down here, on the left side is the longitudinal wave. So I take a giant spring or a slinky, and if I just push on it, what you'll see is a section where it's all pushed together, and then it'll spread out, and it'll be pushed together, and it'll spread out. So the push together section started back here when I pushed on it in the first place, and that wave travels through. So the push together section travels through here, and in between is the part where it's not pushed together. That's a longitudinal wave. The wave is moving with the slinky. If I yank the slinky up and down once, the slinky is still going this direction, but the wave is going up and down now. So that wave going up and down is perpendicular to the direction this is going. We're going to jump over this because we already talked about this. A transverse wave, which is a more typical wave that we'll really usually talk about. The point on this slide is really that the amplitude, the height, how tall the wave is, how big it is, tells you how much energy. So the more energy, the taller the wave. And you can think about waves in the ocean or whatever and see this. A regular wave doesn't have a lot of energy. A tsunami has a huge amount of energy, and a tsunami is much larger. Okay, now what we haven't talked about yet is a longitudinal wave, and here is what I was talking about before. So you push on it here, and that pushes the slinky together, and then it kind of moves through there, the wave moving through, and there you see the push together part and the part that's spread out. One wavelength is from the end of the spread out part to the end of the spread out part. That's one whole wave, that's one wavelength in a longitudinal wave. Compression is where it's pushed together, so when you compress something, you push it together. And the other part, when it's spread apart, is called rarefaction.